is astronomical. And for good reason. There are a lot of stars. On a clear night, and with good vision, we can see about 5,000 stars, only a tiny fraction of our galaxy's 100 billion. 100 billion is undeniably a large number, but as humans, we have exceeded even this. In 2022, Micron Technology launched a 232-layer VNAND chip containing 5.3 trillion transistors, each connected to the larger integrated circuit by 3 wires of only 3 nanometers width, for a total of almost 16 trillion connections. Words about this scale begin to lose meaning to those of us unused to dealing with numbers in this realm. And yet, this unimaginably large number is only about a tenth of the number of synapses or connections in a human brain. The brain is enormous, a genuine galaxy unto itself. And the synapses of the brain are far more complicated than computer circuits. The transistors that are the elemental unit of a computer's integrated circuit can exhibit one of only 2 states, on or off, or in the language of computer science, 1 or 0. The values are discrete, uniform, and repeatable. They are digital. The neuron and its multiple synapses are nothing like this. The connections between brain nerve cells, or neurons, are what we mean by synapses, and they are roughly analogous to transistors in our example. Each neuron can have as many as 7,000 of these synapses, connecting each of these cells to 7,000 neighbors. But in stark contrast to the uniform and discrete connections of the integrated circuit, different synapses can exhibit different degrees of influence on the state of the neuron. The system is intrinsically analog, and, on top of this, it is not even static. That is to say, that the influence that a particular synapse has on a particular neuron can, itself, change over time. We call this influence the synaptic weight. Synaptic weights, the connections, are strengthened and weakened as a result of reinforcement, and this is the mechanistic basis of learning in the brain. Synaptic strength and neurotransmitter dynamics add an additional layer of subtlety, of computation, to the dynamics of the brain. It goes without saying that these circuits and these synaptic weights are not random, that they serve precise functions and demand a complex architecture. But from where does this architecture come? Where is the blueprint? 6 years before Henry Markram's TED Talk, another science megaproject reached its culmination. The Human Genome Project received $3 billion in funding from the National Institutes of Health and the Department of Defense, with the objective of sequencing, that is to say mapping, the entire human genome, the collection of genetic material of our combined 46 chromosomes. In the event, the project sought to map a human haplotype, or half of our paired 23 chromosomes, for a representation of the entire genome within 15 years. At its conclusion in 2003, 92% of the genome had been mapped.
I'm sure in the podcast you probably got the computer and the thing. It could be just doing.
Described to the public as the Book of Life, our genome is composed of